finally start, as usual with a summary. So what we did last time, we looked at general Newton-type methods for root finding. So the problem we are concerned with in this section was f, a big F, which is a function of some variable w, and we want to find a root, and we want to find it with a Newton-type iteration. That means with some iteration where we say wk plus 1 is equal to wk minus, and here we have the residual, the one that we want to bring to 0, but we pre-multiply it with an approximation of the inverse of the Jacobian, or the inverse of the approximation of a Jacobian, and this thing is given mk to the minus 1. And now, depending on how close this mk is to the true Jacobian, where our true Jacobian was jw, and mk should be similar to that. And depending on how close it is, we might have faster or less fast convergence, or not convergence at all. That's actually the main interesting thing here. And we cover implicitly, of course, also the case of a Newton's method when these things are equal. In this theorem that we have proven last time, there were two crucial assumptions, and I want to actually restate these assumptions and today introduce them in a slightly weaker form, which is a form that sometimes people use. So the assumptions are actually an omega condition. We call it like this, because the constant involved is called omega, and the other is a kappa condition. And I want, before I summarize them, I just want to make sure that we really know what it is. The omega condition is actually a condition that is Lipschitz continuity of J of W. That's it. That's actually already it. I could just have said that, but I want to say it in a slightly weaker form, and that's why I use the more complicated formulas that I have. And the kappa condition is a bound on JWK minus MK. That's it. But these bounds would not be easy to use in the proofs. If I would just say this should be smaller than 1, for example, then it's absolutely dependent on which units I choose. I will talk about affine invariance in the next section. So that's why we have chosen a different condition. So this is just a snapshot, so just a phrase, how to remember it. Does everyone know what a Lipschitz continuity is? Lipschitz continuity? The mathematicians do, the engineers also. Lipschitz, not everyone. So Lipschitz continuity is basically what we wrote down here, but if I would just say this, then I would just say, and I write it for a moment, that if I have two values, let's say W and some other W prime, and I take the norm of the two, then what I want is that the J of W minus the J of W prime is smaller than this times a Lipschitz constant. That would be Lipschitz continuity of J. But then the question is really, what norms do we use here and what norms do we use here, and so on. And for that reason, we formulated this in a slightly more complicated way. First of all, this L is an omega. The second thing is we are only interested in the points which are iterates of our algorithm. And also the distance to the center point is what matters. So I take actually these things already. So I could call it omega, but that's still not what we did. We expanded these terms from the left and from the right with some interesting constants. And the first one was that we expanded it here with an mk to the minus 1 before we did this difference. Now with the approximate inverse, because that's what we need in the proof. So now we put a norm around this. And I think I should leave a bit more space here because I need more space later. So here we have wk minus w star and then omega, and I leave some more space. And what we did last time was slightly different than what I do now, but it's actually a similar condition. I will actually take here, because what we needed in the proof was actually the distance between this point and a point which is on the line between the current iterate and the solution, W star. So it's actually this distance that we were interested in, and I need to even more space, sorry. And you see already that now we should have a t here, right? So there should be a t, because the distance between these 2 points is actually t, right? T times that. And in order to make it even weaker, we would require this only in one direction, and that was the only thing that we really needed in the proof, where we also multiply this already with the direction between wk and w star. And now I'm ready, but here I need to add a square because we have another time this distance. And so now my inequality, this is what we really needed. Yeah. So a long story. This is now already new stuff, so it's not recalling anymore. We needed basically a bound on the distance between j and j, but we need it actually only in certain directions, and that's what I want to stress here, namely only when it's multiplied with some directions. And in order to make these conditions as weak as possible, and not just make a blanco assumption about something being equal in any norm, I actually made what I really needed. But in summary, it's a Lifshitz condition on j. Yeah, so you see that this t and the wk minus w star squared, this comes only because we have here this and here the t. Yeah? So that would be the weakest, the weaker form, and that's what we would need in our proof only. And we can also have a weaker form on the kappa condition, and the kappa condition, as I said, is a bound on this distance, right? What we already had last time was that we multiplied this distance already with this inverse matrix here in order to get rid of some of the scaling issues here, because if you scale your function with 100, yeah, then this difference would also increase with 100, and then your kappa would just immediately be 100 times more, but we want it to be smaller than 1. So it would be a very stupid condition to ask this thing to be smaller than 1. That's meaningless. We need to first rescale it, but even to make it weaker, because later on, so this thing we said last time should be smaller than this kappa. But in order to make it even weaker, we actually need this only in the directions again, which are the distance from our final point. And if we have this term here, then we should of course also have this distance on the left side. Yeah, so now this would be a weaker condition on this kappa condition. And if this kappa is really smaller than 1, that's what we need, only then the iterations will locally converge. So that was sorry, it was a sufficient condition, I should say. So if this kappa is smaller than 1, then the iterations will converge, but we formulated the sufficient condition in the tightest possible form for our line of proof. Yeah, at the very end, what you could say, Newton's method converges if Newton's method converges, but that is a tautology, and then it's not useful anymore, right? So we try to make it a bit more separate. So one is a Lipschitz continuity of J, and the other is a similarity of these two things, but then we made it as specific to what we need in the proof as possible. Yeah, but by stressing that one is a Lipschitz continuity, when would you expect this J to be Lipschitz continuous? Actually, you would expect it already to be Lipschitz continuous if the J has a derivative. Yeah, if, for example, J is differentiable, it will have a Lipschitz constant on every compact set. So then in some region around the origin, around the solution, this would be not a restrictive assumption at all. So it will always be satisfied closely enough to a solution. If we have, if this is continuously differentiable. The kappa condition is much more difficult in some sense because it's implicitly assuming something on our choice of these M matrices. And this is where the Newton type methods really differ, where they have different meanings. And yeah, we will have to look at this in the specific case of a Newton's method. But what I already want to say is that if you make, for example, this M, yeah, one stupid thing to do, what would be really stupid as an iteration and which would surely not converge, is if you take for M the negative Jacobian. Just assume the right Jacobian would be the good thing, right? But you could also say I take the negative Jacobian, yeah? Just make it the wrong slope. And this will surely not converge, and you can easily see when you have j, here the minus j, it's 2j basically, then divided by 1j, so to say. Here you have the inverse, so then 2 is remaining, and you see already that the kappa will be 2 immediately, right? When you do the negative Jacobian, which would be a stupid choice. Then it would surely not converge. It's intuitively clear, but you see that the choice of what we choose as a Jacobian approximation would make a big difference here. And the one choice which makes this thing always 0 is the exact Newton's method. That's what you remember. If you take the right Jacobian as m, then everything is fine, and this kappa condition is trivially satisfied with kappa being 0. Okay, I think we did the proof already, so I will not restate it. So this is a weaker form. This is also a weaker form. And one thing which we should also have more weaker, because it's more realistic, is actually at the end, when you have here your space of w's, let's say, that's the space of w's, and here's your solution w star. At the moment I made these assumptions on the whole space, which is of course very, very restrictive. Not many functions will satisfy it, but I actually need to just assume that there's a ball around my solution, and this ball will have even the radius, so it's a set of all w which satisfy the condition that w minus w star, that this thing is smaller than, you remember there was this 2 minus 1 minus kappa divided by omega. Yeah? So if in this ball, so you have a ball of this radius, and on this ball you should have the kappa and omega properties. If this is the case and you start inside the ball, then you will converge. So that would be a weaker form for our assumptions. Maybe we should have stated it in this weaker form directly, but in the original statement I didn't want to clutter you with this t and with this square, which would make the meaning even more difficult to grasp. Okay, so bottom line is Newton type methods, if you start them close to a solution, Newton's method will always converge in practice. If you have a differentiable j, so that means actually that your function must be twice differentiable, then Newton's method close to a solution will converge. The region can be described by this. For Newton's method the kappa is 0, so this will be 2 divided by omega, simple. The general Newton type method might or might not converge, and that depends really on this distance, which also still exists at the solution point itself. So even if you're arbitrarily close to the solution point, there might still be a remaining distance between j and m. Yeah? Actually, there will be a distance if the m is not the Jacobian. And if this distance is too big, you will not even have local convergence if you start even at the origin. You could even diverge. Yeah? Origin, I don't want to... I say origin, but I meant the fixed point, or the solution, the root w star. There's already, I mentioned darkly, or I mentioned that this m that I multiplied because I would otherwise not have the same constant when I rescale my equation. So I want to discuss this concept of affine invariance with you, which is a very important concept in Newton type methods and in applied mathematics in general, I would say. So I want to discuss it with you. So it's one of the big principles in all mathematical sciences is that you should become independent of coordinate systems, right? So that's like what we should always aspire for all our methods. And also for Newton type methods, this is a desirable property. So, so let me just say a definition, yeah, but it's a long definition. Maybe I first say, we regard a Newton type method for a root finding problem, which we still state like f of w should be equal to 0. And if you think that this root finding problem could be something like, let's say you have some ingredients in a chemical reaction, and if you choose some settings, then the temperature of this chemical reaction will be something, or the equilibrium temperature of your reactor will be something, and you measure the something, which is the temperature. You say this temperature should be exactly 80 degrees, and then you try to find, for example, the heating power that you need in order to get the temperature of 80 degrees. Such a thing could be a typical question. But now what you could do with your temperature is you could measure it in Celsius, in degrees, in Fahrenheit, and what you would not like is that when you do it in different units, that your algorithm does different iterates. So what you want is that your algorithm does the same iterates if you rescale actually your root. And also if you choose different variables for your inputs, let's say the heating power you could measure in watt or in microwatt, then you would also have different units. And so what you want to compare it, you want to compare it with a Newton's method, which you apply to a rescale problem. And because I want to be clean here, will just define a new rescale problem, which I call f tilde of y, which is equal 0. So, and I compare it actually, and compare the two with this root finding problem, and here I will actually choose something where I change my f tilde is my f tilde of y is given by a scaled version, which I scale with some invertible matrix at the beginning. I call it A. I apply to my f, and then my y I get actually from my w I get from a linear affine transformation from y. So here I put in a b plus big B of y. So this is something like a definition of a function. It's a new function, but this is not just an arbitrarily new function or something, but it is with A, B, they would be elements in Rn cross n, and they would both be invertible. So they're basically basis transformations. And so what I do here is I basically express my same equations in different units, you could say, or I even mix some of the inputs by rotating a coordinate system. So if you want to find an equilibrium position of something in Earth coordinates, if you measure this in a rotated coordinate system with different units, it should still be the same. So that's why we admit very general transformations. A and B could be any matrix. It's not just rescaling of variables would be a diagonal transformation. Yeah, it could be more general, and that's why we call it affine invariance, is in particular because this term is affine. Yeah, I don't allow an addition of a constant to the whole function, because then, of course, 0 will also change by this constant. That's too trivial. So I will not regard that. But basically, this is the same problem in a different coordinate system, and what you expect is that the iterates would be the same. And what would it mean, actually? You say what you would like is that in the new coordinate system, your iterates are the equivalent iterates, but equivalent means that y and w are related with some relation. So what you want, of course, that wk is equal to b plus byk for both methods. Yeah. And so let me just define what we define by affine invariant. So a method, an iterative method, generating iterates w0, w1, and so on, for f w equals 0 started with w0, because we also need to think about the initial value, is called affine invariant. If you could start the same method add and apply it to this affine problem. Yeah, if it generates the points y0, and now we should just reverse these things. So we reverse this by just getting here wk minus b, and then b to the minus 1, and here we do w0. I do it with a k, sorry. When solving f tilde w y equals 0, and started, of course, at the corresponding value at y0, which is just this b to the minus 1 w0 minus b. So please note that w0 has a double meaning here. It has only one meaning, but it's actually an input to the algorithm. So you basically have an algorithm that's a root finding algorithm. You provide it with a function f, and you provide it with an initial guess w0. And then the algorithm starts generating iterates, and if the same algorithm, when you provide it with this initial guess and you give it this function to solve, if it then generates the same iterates, which are basically the rotated iterates in the new coordinate system, then you call it an affine invariant method. So it's a long description for a relatively simple concept. What we will actually prove is affine invariance for the Newton's method, and later on we will discuss that some of the methods are and some others are not affine invariant. So let me just look at Newton's method. Newton's method is the paradigm of an affine invariant method. So but it's only the exact Newton one, actually. So what does exact Newton do? It generates the iterates according to this. Okay, so that's the iterative rule. And now what we just want to see is that when you start, so this is the thing, and then you start with w0 as the start point, right? So that would be the method that you do for the original problem. And now what would be the method applied to the other problem? It would be yk plus 1 equals yk minus j tilde of yk times f tilde of yk. And your starting point is y0, but we know already that this will be b to the minus 1 w0 minus b. To make these two things equivalent. Otherwise, we would not expect they. But now the question is, do they generate the same iterates or not? And in order to check this, we would actually expand the j tilde and just look that it can then be translated into, if this and this equation are, so to say, equivalent versions of each other. We can just check that. And in order to check it, I will actually use the definition that we had. And so I will work on the second equation. So what will be the j tilde? Let's just compute it here. What is j tilde? J tilde at y is equal to the derivative of this whole thing, but by the chain rule it will be a times j, but j evaluated at the point that is b plus by, right? And then it's multiplied with a b. Right, that's just the derivative. I hope you agree with that. It's chain rule, right? So we have this function definition above. And the f, we had already the formula, and now we see this sorry, here. There was a minus 1 missing. Very important. Did I forget it somewhere else today? No, I think now it's okay. So let's expand these things, and what we get is yk plus 1 equals yk minus, and now, okay, now we get it. So, sorry, the j tilde to the minus 1 will be, of course, b to the minus 1, j at b plus by to the minus 1, and then a to the minus 1. That's the easy thing. And now we get this beautiful thing if we expand this with that expression. We will have here, of course, a b to the minus 1. Then we have a j at b plus byk. And then we will have here an a to the minus 1. Here we will have an a. Here we will have an f. And then here is actually b plus byk. So that's now the expanded form of that whole thing. This one gives a unit matrix, so that's already good. So something simple, something nice. Huh? But then there's this this whole b thing here, right? And so what we could do, if we want, we could just try to translate this equation into a w equation to make sure that it's equivalent by multiplying the whole equation with a b at the front, right? So what we could do is we see that actually b yk plus 1 equals byk minus j at b plus byk to the minus 1. Here was a minus 1 missing, sorry, minus 1 times f of b plus byk. So now we have it still not exactly the right thing, but what we could now do is, of course, we could add on both sides a b, right? So here we can add plus b, and here we can also say plus b. And then we are ready, because then what we get is actually b plus big B yk plus 1 is equal to b plus big B times yk. It's equal to, with minus, and then here b plus byk to minus 1 f of b plus byk. And beautifully, we see that this is exactly, that was wk, right? And that was wk plus 1. And so here's wk, and here's also wk. And so we see that this equation is exactly equivalent to that equation. And they are started at exactly the same point. So we have equivalence of the two iterations. Or not equivalence, they are identical. If you would now take, for example, just no matrix here, the whole thing wouldn't work, right? So if you would just take, for example, a unit matrix as your Jacobian, which in some cases might make sense in some problems, but it will not be affine invariant, because what would happen is, we will never get this A here to cancel things out. So this is one method that is affine invariant. And some other methods are surely not affine invariant. Do you want an example for a non-affine invariant method? Or, I mean, it's how do you prove that a method is not affine invariant? You just initialize it with the same point, and then you look that the first iterate is different, and then you see already that your method cannot be affine invariant. That would be the way to do it. And do you want me to do it with one example? Okay, yeah. So let me just say I do it not for a general method, but just for a scalar method, maybe even. Yeah? And it's a simple root finding problem. So we have actually a function f. So a counter example. For Newton, for affine invariance, and it would just be Newton type with a fixed with m k equal to the identity matrix. It's a nice matrix. It means that here we just have to have the iteration will be just wk plus 1 equals wk minus f of wk. If your function f is something that monotonously increases, this might make sense in some contexts actually. But what will happen if we apply it now to this inverted problem? what will happen here is that we have yk plus 1 equal to yk minus a f of b plus b yk. And so now we would like to transform this into this new coordinates, or back to the w equation, and we can now see what will happen. Yeah? So here we have just the same method applied to this thing. We do the same tricks as before, so we multiply everything with a b, and we add a b to it. So then we have here b times yk plus 1 equals a b plus b yk minus, and then here we just added this once, but here we will have b times a times f of b plus b yk. So what will happen is that this is actually wk plus 1. This is wk. This is wk. So it nearly looks like the method before, but there is a strange matrix in between now, that's b times a, which usually is not a unit matrix, right? So if you do this same iteration with always choosing a unit matrix because you think a unit matrix is a good choice or something, then in the new coordinate system you will have implicitly chosen another matrix, namely b times a. Yeah, so this is equivalent to an iteration where you say wk plus 1 is equal to wk minus ba times f of b plus byk. So your simple unit matrix is actually not affine invariant, and if you change your coordinate system, if you rescale your problem, then you will actually do different iterates. Is there a question already? So then you have here a funny matrix, and depending, you can easily see that it really matters how you scale your equations, how you choose these matrices, and so on, right? So sometimes this might be converging well, and sometimes it might not converge. Good. So questions we will treat in the next exercise sheet, not in the one of today, is Gauss-Newton's method affine invariant, for example? And in order to apply this whole set of thinking to our optimization methods, we first need to transfer the knowledge that we gained for f and w. We need to bring it back to the optimization language where we want to minimize a function. So let me just say what we have now in the next section is about local convergence for Newton type optimization. Yeah, so it's about optimization again, and we will actually apply all the things that we had before. So we will regard. I think I can prove these things using the same assumptions as before. So I just make a theorem which we call 3.2, and it says that we will actually generate xk plus 1 equal xk plus pk, and xk was the current iterate, pk was the direction. Pk we got actually from something with a minus sign with these Hessian matrices and then the gradient of an objective function. That was our direction p. Yeah? So maybe I should first say what we regard as a problem. Minimizing f of x. And I just recall the Newton type optimization methods we had before. Yeah, so this was the setting we had, and then we would apply these Newton type iterations. And we assume that these bk's are invertible everywhere. Yeah, so that was an important assumption, otherwise this method is not well defined. But now we will assume that there is, of course, a local minimum. Yeah? X star is a local minimum with nabla f of x star being 0. And then also you assume that your x0 is close to that whole thing. And we assume again such a distance bound, which is 1 minus kappa divided by omega. Yeah? And we assume that these two kappa and omega conditions are met, which in the optimization context I can state now like this. So this second derivative will be here I need every y, okay, sorry, that was the original way. I do it again in the way which is compatible to what we did last time, xk minus y. And the other condition was the compatibility, namely that this matrix here, so it's always this of xk minus mk, bk in this case, bk is smaller than kappa. And I give it actually a kappa with an index k, which should again be smaller than a big kappa, which again should be strictly smaller than 1. And these would be the two conditions. It's just a transferring to the language of optimization. And then we will have that xk is converging to x star. And we will have different rates. And these rates will be depending on these values of kappa. Yeah? So we will have first, if kappa is equal to 0, that means we have the exact Newton. Then we will have Q quadratic rate. If, on the other hand, these kappa these kappa k values go to 0, and this is what happens actually with quasi-Newton methods. Then we have what we call Q superlinear convergence. And the third case is if these kappa values, kappa k, they're always bigger than some constant rho, which is bigger than 1, then this is actually what we will have in Gauss-Newton typically, or also in steepest descent. Then we will have Q linear convergence. Yeah, because we still assume that there exists an upper bound for it, but there's also a lower bound, so the values will not go to 0. So then it will be Q linear, and the proof for all this is extremely simple, and I should say it's just a straightforward application. You just set f of w is equal to the gradient nabla f of x, where you identify w and x. And so and then apply the theorem of last time. Apply the general theorem. So why? Because j of w is then, of course, the derivative of this thing with respect to its own variable, which is actually the second derivative. So, and the bk is, of course, the mk is, of course, the bk. So you just apply the general theorem from before. I just want to tell you a few differences or some things which are a bit specific to optimization. This matrix is symmetric for optimization, while in the general Newton type method it was not assumed to be symmetric. Yeah? This is actually important when we regard affine invariance, because for optimization we would just think of this affine invariance a bit more restrictive. So what is affine invariance for optimization? We have an objective function f, and it can actually just, you can actually have either a function f of x, the one that we have here, And the rescaled version of this whole thing is, I mean, there's one trivial thing that you could do with your method, and maybe it's already interesting. So you could have an alpha, should be a positive constant, right? Because otherwise minimization problems would be maximization problems. So you can multiply this f with a positive constant maybe, but nothing else is allowed. And it should be then applied to some b plus big B times y. So this is something which you could define possibly as a function f tilde of y with alpha positive, scalar, and b invertible. So these would be the only transformations that really make sense for optimization. I hope that you agree. And sorry? Oh yeah, you could add a scalar to this whole thing, right? So we could actually, for optimization, that's very funny, we could add plus beta. It would not change the optimization result either. That's a very good idea, yeah. Nice. So here's the product, and we could still add something, and beta and b would be arbitrary. Beta element in R and b element in R n are arbitrary. And now we could look what this means for the gradient and what does it mean for the Hessian, and then we see already some things. So what will be the gradient of this function f with respect to y? So because this gradient will appear in our iteration, right? So we should have a look what will be happening with this gradient. The gradient will be actually modified with this alpha. So it will be alpha times then the gradient of f, but because the gradient is a transposed Jacobian, I write it here in order to apply the chain rule, b plus by. So that is now the gradient of f. And I need to take the inner derivative, but a transposed one. So I have a b transposed, that's the inner derivative here. And that is actually already my gradient. Yeah, so this would be my gradient now. And if I want to compute the Hessian of this whole thing, then I basically see that here the alpha, the b are the same, and then it's actually just the partial derivative of this whole thing, but that gives me the Hessian of f evaluated at this point times the inner derivative, which was the matrix B again. So you see that if you compare this with the general rescaling that we allowed here in this affine invariant, then basically, first of all, this beta, the additional constant, will not appear anywhere in our algorithm. So all Newton-type methods that work like this, they will behave identical to these additions. So that's a good thing. They will not actually change anything. But here we will, so to say, have this thing could be the matrix A. So, and this is still the coordinate system. So what we will have is a restriction of A that will be always alpha times B transpose. So it will be nearly the same as the B transpose in definition of affine invariance. So, yeah, we could have a short look at one method and see if it's scale invariant or not. So let's just look at the gradient method. So do we think that the gradient method is scale invariant? So what will it do? It will just have xk plus 1 equals xk minus 1 over some step, which I call maybe 1 over gamma. I want to have a new constant here, times the gradient of f of xk. And actually we see that this is nothing else than the method that we have already analyzed before. And we already have seen that that matrix, that this would not be scale invariant. Actually, it will, if you think of it, when we transform it, there will be a BA, and so B is B, and then there will be a B A is equal to B transpose times alpha. So it will correspond in a different coordinate system. It would correspond to a matrix where we would have a very different iteration matrix in front. A very strange Hessian approximation, actually. So it's not affine invariant. See the example before. Maybe to give you a bit of intuition of what scale invariance means in optimization, you could think of a simple optimization problem where you have elliptic level set. Yeah? A gradient method would actually perform like this on this set of. It will always go orthogonal to these lines. Yeah? When you rescale your model, when you rescale your variables with an affine transformation, you might actually be able, under very fortunate circumstances, you might be able to transform it into a new system. So this was W, and this would be Y. And if you're lucky, you actually transform it to a circular system of equations, because circular is extremely nice for optimization, because the direction in which your gradient points actually is the direction which also points to the optimum. So your iterates will go straight to the solution, and after very few iterates you will be at the solution, while here it would take you lots of iterates. So you see that the method can be performing much better if you scale the system nicely, and that's actually what people sometimes call preconditioning and so on. The method that doesn't need preconditioning is Newton's method, but it's of course applicable in different contexts. So you see, if you don't have an affine invariant method, you need to really carefully think about how to scale it and how to perform well. And usually we prefer nice affine invariant methods. Okay, I think the relation between the general result and these convergence results is clear, I hope. So maybe to summarize briefly, what does this theorem say? It says your Hessian itself should be Lipschitz. So that means actually that your function, if your function is third derivatives, continuous third derivatives, everything will be fine. Many functions have this property. And then the second thing is that your Hessian approximation should be similar to your real Hessian. And that is something that we intuitively already said. And when we analyzed Gauss-Newton method, we said there is this error matrix, the difference between the two. Here it gets a bit quantified, so here you get an idea of how big can be this difference. And if you just imagine, and this is some intuition that I sometimes have here, if you just imagine these things for a moment to be numbers, which is of course not the case, these are matrices, but if they would just be numbers, then you see, roughly speaking, that the difference between the two matrices must be smaller than the magnitude of the matrix itself. Because if you have this difference, you divide it, so to say, by that number. So some intuition is that the difference should be smaller than the matrix themselves, than the matrix approximation. But this is all just intuition. And I think I want to leave it like this. That was the chapter on local convergence of Newton's method. So what we have done until now is we just looked at the case when you start close enough. Yeah? And this whole condition that I state here, namely that the x0 should be very close to the x star, and the w, you remember, could be an arbitrarily large number. So this, depending on how big this w is, this could be an extremely small neighborhood. So in Newton's method that you use in practice, you will start somewhere, but probably not exactly close to the solution. You don't even know where the solution is. And now the question is, what can you do? And that is what we will do in the next chapter about globalization. You will actually try a step, and then you modify it so that at some point it actually makes progress possible. Let's do that in the next hour, and let's now make a break of 10 minutes until 3:10. Okay. I just wanted to add one little thing, a little analysis to you so that we can get more intuition about the local convergence, right? So just a remark which is still in chapter 8. So it's 8.4. For fixed matrix M. So I want you to just note one little observation. If you have an iteration of this form, where you have m to the minus 1 times f of w, and you want that this converges to a 0 point, then the kappa condition, what would be the kappa condition? It would be actually that at every iterate you want that the f, the Jacobian of f at some wk minus m times m to the minus 1, this should be smaller than kappa, right? So that was our condition. But actually this is not exactly necessary and sufficient. That was a sufficient condition. Yeah? But if you think of this is actually just an iterative scheme that is can be either contracting or it could be diverging, and we have a much tighter characterization because in this case I fixed the matrix, so the things get very easy. I could also just check if this iteration, yeah? So the question is how to get a tighter condition. And that is actually both necessary and sufficient. And we're assuming arbitrarily close starting points. Huh? So W0 minus W star, very, very small. Huh? So I said that when you start small enough and your kappa is 0, then you would be anyway in no problem. But what will happen if you start actually at the solution and you apply this iteration? And what will happen is actually that you could just say what I define a function which I call it g of w, and this function is given by a w minus m to the minus 1 times f of w. So that's actually one iteration step. So then my iterations are equivalent to just wk plus 1 equals g of wk. You agree? That's just a shorthand to write down what we do. And in order to see if these iterations converge to a point or not, yeah, actually I might make it even a bit, no, it's okay like this. If I want that these converge, a necessary condition is that there is, at the point to which I want to converge, there is no eigenvalue of this matrix, of the Jacobian of this matrix, that's larger than 1. Yeah? So let me just say necessary for convergence to W star is no eigenvalue of dg by dw at W star has modulus larger than 1. I don't know if you are familiar with that result. It's quite intuitive because the Taylor series is a good approximation close to this origin, and either this Taylor series will expand, then you will get growth, or it will actually shrink, and then you will have shrinking. And so it's sufficient for convergence to W star is all eigenvalues of this matrix dg by dw at W star are smaller than 1, have a modulus smaller than 1. So these are two results which are probably quite intuitive for those that are from engineering, and maybe for the mathematicians also. It's like Banach's fixed points theorem and so on. So when you have a contraction, then you will actually contract, and if there is one eigenvalue larger than this, then you will not. So the reasoning is actually very simple. So wk plus 1 is equal to, if you look at the distance, wk minus w star, just without anything, then it will be g wk minus w star. And what will it be? It will be the Taylor series. But what will be the, if you apply, so this will be, that's an identity that I can use, and now I can actually use my fact that this whole thing is actually g of w star plus dg dw at w star times w k minus w star, so that's just the Taylor series of the first term, and then I subtract from this minus w star, but because I'm at the solution, these two terms will be cancelling each other anyway. They will. Exactly, they will. So what I get here is, and plus a higher order term, right? So plus wk minus w star of quadratic deviation, and so what I get here is I get the derivative dg by dw at w star times wk minus w star plus higher order terms, wk minus w star squared. And so you see here's the distance and here's the distance, and if this matrix here has all eigenvalues smaller than 1, then actually you could regard this distance in the eigenvalue basis which corresponds to your eigenvalues, and if all of these eigenvalues are smaller than 1, they will contract, and eventually this thing will converge to 0. If there's one eigenvalue which is larger, and it happens that this component is in the initial deviation, then this will be propagated through this matrix again and again and grow up ad infinitum. So from that point, everything is nice. And I think quite quick to understand. That's more a remark here, but what I want you to notice is that the dg, what is this dg by dw at w star? What is that for the case that we have here? So for this map, it will be a unit matrix. That's the derivative of that. Then it will be an m to the minus 1 from here, and then the Jacobian of this. So that's j at w star. So it's all about the eigenvalues of this matrix, and if you just look for a Newton type method which has a fixed matrix M, and if this matrix has all eigenvalues smaller than 1, then it will converge. If there's one of these eigenvalues bigger than 1, it will diverge. So this way you can easily check for some methods if they can converge or if they cannot converge by just looking at this matrix here. Just a short remark I wanted to make for completeness, but not to spend too much time with it. And of course it was also a bit addressed to Andrea. Okay? Good. So let me continue the next chapter. So chapter 9. Right, it's already chapter 9. So, as I said, this whole analysis was assuming you are arbitrarily close to your initial guess, and then it's interesting how fast will you converge. But the other question that we have is, when we are very far away, what should we do? And that's what we call globalization. And there are many strategies for globalization, and one thing I should just tell you, what we do in this exercise sheet is you just play around, you try different initial guesses and so on, and if you're lucky, you're close enough, and then you will have a good convergence, right? That would be one way. That's not called globalization, that's trial and error, but anyway, it's a way that you can presume, and there are some advocates that say, before you give up, try 10 times with different initial guesses and try full step Newton, because it's such a good method. And only afterwards think about things like globalization. But anyway, you should know what globalization means. And for globalization, I want to come back to this idea of the storyline that you're in the dark and you're in the Swiss mountains, you are lost, you want to go down to the valley, and you can do steps and you notice somehow in which direction is a descent direction. Yeah? And then you can do, okay, this is the artificial thing, your steps, you're a very big guy, so you can do very big steps, and you only know the gradient at the current position, and then you go to another point. But if you jump too far, let's say, yeah, so you're maybe jumping. Okay, it's a bit arbitrary, because an optimization algorithm will just have point evaluations, yeah? So it will not go like we go with feet continuously, it will do very big steps typically. So it can very quickly happen that you have a descent direction, you go down, but your step somehow, because you're so optimistic, you do such a big step that you're on the other side of the mountain, of the valley, and then you're already higher than where you started, right? And then that's what you would like to avoid. But that's where line search comes in. So what you do is actually you have a descent direction, you know in this direction it goes down, and then you say, I try a big step first, but then you see, oh, that was too high, then you try half the step size, for example. Maybe you're going down or not, but you can reduce again, half or half and half, and at some point, because you knew that it was a descent direction originally, at some point you know it will be going down, right? So in that sense, that's what globalization by line search does. And I want to explain what conditions you will have to meet here. So the whole modification is two things. First, you take pk, a descent direction. And you don't care how you got it, but you remember there was a lemma. That means the only thing that we needed was that bk should be a positive definite matrix, and then pk was a descent direction. You remember that? Yeah. So this would be one way. Huh? E.g., pk is equal to minus bk to the minus 1 nabla f of xk. Yeah? So that would be one direction with positive definite ones. This would be the right, a good descent direction. So that is the first thing. And then the second thing is you make your iterations go like follows. You just don't take the full step, but you damp it with a factor that we call tk. And this factor is called the step size, tk. And the step size should be something between 0 and 1. Typically we stop at 1, we don't want to make bigger steps. Sometimes there could be even methods which do even allow bigger steps, or tk, just something positive. So then it should just be positive. Please note that we don't like a step size of 0, so we exclude the value 0 itself, because that would be meaning no progress, and then we are stuck, right? So then we just say, hey, this was a too big step, so I don't move. and then you will never arrive, right? So that's not good. But what we want now is you ensure something. And what you want is that the function values at the new iterate, xk plus 1, should be smaller than f of xk. That's intuitively what you want. But this is a mathematical smaller than, and I just already want to tell you that just being a bit smaller is not enough. And the reason for this is that I could make sure that I go down in a descent direction. Just think you go down in a descent direction, and everything is nice. But my first step, I will just take step size 1/2. The next time I take a step size 1/4. The next step I take 1/8, and so on. So my steps are always getting smaller and smaller. Every single step I have descent, but you remember the series, that's a geometric series which will converge. Every time I make a bit of progress, but the progress is getting smaller and smaller and smaller and smaller, and I will actually get stuck anyway. So even with infinitely many steps, if they get smaller and smaller, I will have a problem. So what I need is that I have a margin. And this margin we need to define. And there are two things. Actually, we want the steps not too big, right? Let me just say that I do it in the same order as in the script. So tk should be small enough to ensure descent, so you should avoid going on the other side up. But also they should be large enough to ensure progress. So progress, so that you really have sufficient progress, right? And the pitfalls that you would have from this criterion, I will keep it in just in quotation marks, is that you could easily think of a situation where you would, as I said, so you would have this thing, you start here, you always have the same step in this direction, it's always a descent direction before you are here, right? That would be your x, here is your current iteration. And if you do small steps and you make these steps smaller and smaller, for example, like this step first, then half a step, then a quarter step, every time you will descend, and then you converge somewhere to this point. So that would be a nasty method. You could also have something which is even nastier in some sense. You could actually make sure that you are, so here's the line where you have the same size, but you could make a step which is just so big that you arrive here. It's a very big step. It's actually somehow making progress because you really go down here, and then you go basically here. You could make another step that brings you here, and somehow you make progress in every single iteration, but you make less and less progress, and at some point you will be in a limit cycle jumping from here to there, and every single step you will do a little bit of progress. So these would be two pitfalls. One is too small steps, the other is actually too large steps, and somehow they don't make sure that you, and you can still have, with large steps, you can still not have enough progress. And in order to avoid both situations, people invented line search conditions. Yeah. They need to ensure both. Ensure both A and B. Yeah, so small enough to ensure that you really go down, and large enough so that you don't get stuck here. And what these line search conditions do, there are many of them, but nearly all conditions have one of these two conditions. And I will give you Armillo backtracking. And that's a default algorithm that will actually give in practice quite good results, and that's very often used. And there are two conditions actually. One is that you first make sure that for A, so to make sure that you make small enough steps, you will actually require this, but with a real margin. And the margin is that we say that actually the function value at f of x plus tk times pk, so that's a new function value, this thing, should be not just smaller than the old function value at f of xk, but it should be smaller than a kind of Taylor series approximation of the old one, which I will, the Taylor series would be this, it would be nabla f at xk transpose pk. Yeah, that was our Taylor term. But of course, when we have a t here, we need to add a tk here, right? And that would be our Taylor term. But we will actually, that would be this condition, all right? But that one, you see already from this example, you cannot expect to be below the Taylor series. What you can expect is that you are below this thing or any line between. And what people choose is, so to say, a fraction of this descent that you get from the Taylor series, and they introduce a constant which we call gamma here. With gamma typically smaller than half. Gamma element in 0 and 1/2. Yeah, so you allow some, usually it's like 0.1 or even less. So it's a very small number, so it's very close to just nothing, right? So just descent, but a little margin which becomes bigger the bigger your step is. So you require actually that when you do a long step that you are really significantly lower. And when you have a small step, you're not. And it's clear that because your Taylor series is a good approximation when you have this extra factor gamma to make your, so this is for gamma 1 we would have the Taylor series. So this is gamma, and this would be gamma equals 1, right? Gamma needs to be smaller than 1 in order to bend this curve up with respect to t. And then we require this. So this was to remind me that I should end in time to avoid breaking promises. And I think I will finish in a few minutes. And this condition that I just mentioned is called the Armio condition. And in nearly all line search algorithms, this condition is used. But this will not make sure, I mean, I could still choose an arbitrarily small t, so that my iteration will actually just make arbitrarily small steps and not make progress. And then the other condition, in order to get this step big enough, in this special choice, we do backtracking, so that we do exactly what I described. So you first choose 1, and then you make it smaller. And here we choose a constant which I call beta, which is smaller than 1 and bigger than 0, of course. And this constant is actually, you start with t equals 1. And then you will actually reduce t. You check the Armio condition at xk plus t times pk, if it's satisfied for this value of t. And if it's yes, then you're done, you're finished. And if no, then you reduce t by t times beta. And so you reduce it with a factor of beta. For example, 1/2, as I said. So you try it. And the first time you measure it, then you stop line search. So actually it means that you will not continue backtracking when you have already found the first point that satisfies this condition. So to give you an example plot, I think this plot is now actually the function that I plot here is f of xk plus t times pk, and this is t. So I plot it as a function of t. If t is 0, I'm at the original value, and I know this is the Taylor series, but my Armio condition, as I said, is something between the Taylor series and the horizontal, so it's, let's say, this thing. And so all these points satisfy the Armio condition. Let's say my full step, so t equals 1, here was maybe t equals 1. Then I first try this value, Armio condition isn't satisfied. Maybe my value beta was 1/2, right? So then I reduce my step to 1/2, and then I check if my Armio condition is satisfied, and indeed it is. I am now lower than this approximation. And at that moment, it means I take the step. I will not do another backtracking step. If I would do that, then I will violate, so to say, this condition because then I could do 5 or 10, and then my steps might be too small. So this is actually the two things. I require the Armio condition, but at the point that I choose, I know that if I would have that the previous point that I tried was not possible. Yeah? So I do either the full step and it was already satisfying the Amio condition, or I do something where I track back so long as necessary but not longer. Okay, and these two things are important. And we will need that in the convergence theory. That's it for today. So you have the idea of what is a line search. We will prove global convergence with line search later. But today, actually, you're already able to implement a simple line search algorithm if you want. You have the idea. Okay? You don't need it for this sheet, but for the next one we will need it. Thank you very much. Have a nice weekend.